Let's wait for a few minutes. We'll start by 3:05. Today's session will be related to current years. We'll go through a little bit of basics, and then we'll solve the questions related to concepts. We are waiting if anyone will join, then we can start. And we'll discuss it. Okay, so this is a weekday. Before we start, as I said, this is a session related to current news. So before we jump to the numericals, let's first see why we need the current news. Okay, so let's just have the introduction. What are the advantages? Let's just look. Okay, we can have two sources, right? Voltage source, and we can have current source. Now, if I look at the MOSFET, it can be biased either by current source or voltage source. Now, if I apply a voltage source, that has to be applied at here, at this point. If I apply a current source, that has to be pushed through here, drain side. Let's say this is the end. Okay, so now we know IDS for this transistor, since it is in saturation, IDS will be given by Q W by QL UGS minus VGH whole square, and GN, that is d by ds by VGS which is given by KW by L UG plus minus VGH, right? Or now, or it can be, let's call this as 1, and another definition for G will be if I multiply and divide it by VGS, it will give me, to solve this, we will find it as this formula, A W by L times IDS. So in terms of IDS, we can write it this way. And these are the two equations. Yeah. Now look here, if I, now, the threshold voltage, it depends on external factors as well, such as temperature. If temperature changes, in MOSFET, In MOSFET, we have intrinsic carriers. This is P hold are the majority in P wave. So we get the carriers here in the inversion, right? In the new device arrangement. So what can happen is if temperature change, this is a band diagram, and if it is a P wave, so this is acceptor level, this is EV, this is EC. So depending on temperature, this EA level can be and let's say we have the Fermi level. EA level can be occupied or not occupied, depending on temperature, right? So what can happen is if temperature goes very down, temperature goes very low. In this Fermi level, the Fermi level definition of Fermi level is the clear definition is levels below EF are occupied, right? So if the temperature goes down, it becomes difficult for these levels to get ionized. So that means this Fermi level goes below the acceptor level. Similarly, if your device is PMOS, this is ED here, if temperature goes down, then it becomes difficult for these electrons to jump in, and they will remain in their ED level. So your Fermi level will be somewhere here. Okay. Yeah, right? So if these things change, it will eventually change your VTH, that is threshold voltage as well, because threshold voltage is threshold voltage is if this is my EC, this is my EV, this is intrinsic level, this is Fermi level. The threshold voltage is the applied bias at which so this is by F, this is by F. Okay, so this is your definition for your EC EV. Okay, this is not up to the scale, but we can just understand it. Just for the understanding, this is the time right there. So this EF depends now on the temperature. Position of the EF depends on the temperature. So does now not actually the EF. EF doesn't directly depend on temperature, but it is the uh, distribution of the ionizing carriers. Sorry, not distribution, occupancy of the acceptor of donor. So depending on that, your Fermi level will be positioned right. If they don't get ionized, your Fermi level will be close to your in between the levels such that they are not occupied at all, and that will change the pressure voltage characteristic of the device. Another external factor is let's say you have mm, that you may not have studied those effects. That's called as a mm, let's say initial effective oxide thickness with oxide thickness change. One of the effect is polar diffusion effect. If you are interested, you can learn about it, but it's not important currently. I'm just writing the case of what are the external factors. Now, these are some of the things that change your threshold voltage. Another thing is doping also change DTH. Okay, your oxide thickness Tox. Okay. If there is short channel effects may also change. Okay, 1 second. Okay, so now let's go by using the definition of GM. We found that GM is equivalent to K W by L VGS minus VTH. Now, if VTH by some external factors it changes to VTH plus delta V VTH. Okay, so you can write GM dash will be equivalent to K equal to by L VGS minus VTH minus delta VTH, which will give me GM dash will be equivalent to K W by L VGS minus VTH minus K W by L delta VTH, right? So this will be GM dash is equal to, let's call it as GM naught, it will be equal to GM naught minus K W by L delta VTH. So this will be delta GM is equivalent to K W by L delta VTH. If I divide both sides by delta GM naught, I will get as delta VTH minus. So, if there is a change in the VTH, there will be corresponding change in delta. That there will be change in the characteristics, device characteristics, and that is given by this equation. Let's call it 3. If there is change in this was a case when there was a change in VTH. Now, if the change is in mobility, mobility can change as well, right? Scattering effects. There are scattering effects in the device, right? So let's say mobility change from mu to delta. So what we will get G in okay, let's first write it as KW by L which is minus VTH. Here K is mu Cox, right? Yeah, Cox. Now if mu change to the it will be given by mu plus delta mu Cox W by L VGS minus VTH. So my Gm will be Gm naught plus delta mu Cox W by L VGS minus VTH, right? So it will be delta Gm. If I divide it again by Gm naught, so it will be delta mu by mu. So again, it is quite sensitive to change in mobility. Now, coming to the main point, why we use current sources? Why should we use current sources? Now, by using a constant current source, we know from equation 2, Gm is equivalent to 2 times KW by L IDS. This goes to this. Okay, let's call it Gm naught. Now, if VT changes, there is a constant current source here. This is constant because it's external bias. IDS is fixed. So there is no change in Gm if there is a change in delta VTH. Therefore, delta Gm is 0. Right? So this is a big advantage, right? Next is if mobility change. How mobility change you can do is Gm naught is 2K. Sorry. 2 mu C of W by L IDS. And the dash will be equivalent to 2 mu plus delta mu C of W by L IDS. Okay. So it will be under root of 2 mu C of W by L, right? IDS 1 plus delta mu by mu. Right, C2, this is G dash, this is G naught, 1 plus delta mu by mu is given by 2. Okay, so if I use the binomial expansion, I will get G naught 1 plus delta mu by 2 times mu, which is at 1. So my G dash will be G naught plus delta mu by 2 times. That will be delta Gm delta mu by. Okay, wait, there is one mistake here. 1 plus okay, so this will be doing that by Gm naught is equal to 1 plus delta will be given by Gm dot by Gm. Next one is delta mu which is delta Gm by Gm naught delta mu. So sensitivity drops to half. Quite an element, right? So current source seems to be more useful than bias transistor. As an advantage with respect to its transconductance. G, right? Let's just see one. Now current measure. How do it happen? If I have a transistor here and I have another transistor here. So if a current of RDS is equal to 1 ampere flows, the current mirror but definition will be this is M1, this is M2. The same current of 1 ampere should flow in this device as well, right? So your bias transistor, let's say this transistor is biased in such a way by using current source. There is a current source and a bias it, let's say by 1 ampere. Okay, let's say this is VDD, and okay, now I connected another transistor like this. Now look here. If a current of 1 ampere is flowing, right? So it will flow through here as it's fixed by 1 ampere. So it will flow through the device as well, right? Let's first assume how it will work. Initially, when I apply it, the current of 1 ampere for the transistor and it is connected, right? So there is always an external capacitor here, right? Now you should understand that initially IDS is 0 and now I apply a current of here as IDS. ID, let's call it ID. So when this current comes and it sees that no current is in the device, so the capacitor voltage, let's call this as VC, when IDS is 0, right, capacitor and ID is non-zero, the capacitor voltage VC will start to increase. So as ID is fixed to 1 ampere, and corresponding to that 1 ampere, the capacitor voltage will keep on increasing till it turns the device on. See here, if VC will go on increasing, it will increase the VG as well, right? And once it increases, it will reach the threshold voltage and the current starts to increase here as well. So since the current will start increasing, then VC voltage will keep on increasing till ID is equivalent to IDS. So it will bias this, we bias this MOSFET transistor using a current source, and we use this study how it would change the potential here at this node, and that will apply it here as well, and it will turn on the device, and then once ID is equivalent to IDS, then the capacitor voltage increase will stop. So this is the principle here as well. So it will increase the potential here that will be applied here, right? Now let's say 1 ampere. Let's use a definition. IDS is equal to, let's call them as identical. These are identical transistors. They have KWLC to L VGS minus VTH. Let's say VTH is equivalent to 1 volt. IDS. Okay. So now it is 1 ampere. Let's treat it as 2 milli. It is 2 milli. Let's say it is 1 milliampere. Just get an easy answer. 1 milliampere. Let's say this is 2 milli by 2 milli. Here VGS minus 1 millimeter by 1. So so VGS minus 1 is equivalent to VGS square minus 1 is equivalent to 1, and then VGS will be equivalent to 2 volt. Now this potential is 2 volt. This 2 volt gets applied to this transistor as well. M2. And for M2, the IDS is again kW by 2L VGS minus VTH. Okay. Since these transistors are identical, right? These transistors are identical, and now the IDS will be simply 2 milli by 2. This is 2 minus 1 whole square. Here we go. This will be IDS is equal to 1 milli into 1. That's 1 milliampere. So the current of 1 milliampere will flow to this transistor. Okay, this is how it works. All right. So this is a very simple example how current mirrors work. Okay, so now that we understand this, we can just go to the questions now. Okay, this is a you may be frightened to see the multiple answer, but you will see that these are very easy questions. Okay, I have taken only the here we only study the MOSFET. And let's see what does the question say. Okay, Kw by L for the transistor is given, VTH is given, lambda that is channel length modulation, VTT, I reference is 2 milliampere. Refer to the circuit, find the DC voltage V3. We have to find this voltage between M3, okay, such that the current of 2 milliampere flows through. Okay, this is your source, and this will be your current measure. Okay, this should have a same current in both directions. Okay, let's start from M4. Let's take M4 as an example here. So it is an NMOS. IDS will be kW by 2L. That's straight. Every transistor is in saturation. It's already a drain connected, so it will be in saturation. You know, drain connected. We know for saturation, VDS should be greater than minimum. It should be VGS. Here VG, S and VDS are equal. So VDS will always be greater than VGS minus VDS, so it is always in saturation. So this will be VGS minus VTH. VTH is for all transistors is given to us as 1, so IDS is 1 milli by 2 into 1. Sorry. This is VGS minus 1 whole square. And IDS is 2 milli. 1 milli by 2 VGS minus 1 whole square. This will be, since for it's an NMOS, we will take square root and we will take only positive sign. And VGS minus 1 will be equivalent to 2, VGS will be equivalent to 3 volt. Let's call it VGS 4. Now, from this node to this node, it's 3 volt. From this node to this node, it's 3 volt. Okay. Similarly, for the same current to flow in this transistor, this should be also 3 volt. So if this is 3 volt VGS, then if this is 3 volt, VGS4 is 3 volt, which means VGM4 minus, let's treat this as VG1, VG1 is equal to 3 volt. This means VG4, since VGS is ground, then this will be 3 plus 3, is equivalent to 6 volt. So VG4 is 6 volt. Now, say it has to mirror on this part, then VG4 will be equivalent to VG3 equivalent to 6 volt. Okay. Now, uh, we have to find V3. With, from circuit, we should get an idea that V3 will be directly equivalent to what is the potential here, that is 6 volt. So direct answer will be V3 is 6 volt. But how do we get that? We will just see. Okay, wait a second. Okay. Now your VG S3 will also be equivalent to 3 volt, right? That means VG3 minus VS3, VS2, that is here VS2, that is V2, will be equal to 3 volt. And VG3 is 6 volt, so your V2 will be equal to 3 volt, right? Now, for the device to be in saturation, V3, that will be the minimum case. We can just directly write it. V3. Yes. So V3 is directly V3 minus V2 if sorry, V3 can be directly written as VDS of M3 plus V2, right? Let's just use a current mirror method. Since this transistor, Okay. So for same current to flow, drain potentials should mimic as well, right? So now, if if they should mimic, then this potential here, let's call it as V1, should be equivalent to V3. Then V3 is equal to V1. That will be simply given by what is the potential here to here, that is VGS M1 plus from potential here to here, that is VGS M, sorry, this is M4, M4, M1. That is 3 plus 3, 6 volt. We directly wrote here V3 and here as a 6 volt, then we could have directly answered this as 6 volt. Okay. Okay. Next is that we have been doing for long. Let's do the same again in this numerical. What we have to find is resistance. Looking input drain terminal and 3. Okay. So what we have to do is for equivalent circuit. Just look here. We don't need to draw the whole circuit, but for the purpose of clarity, I will just draw the whole circuit. But see, if here is a ground here and your applied voltage will be 0, then you can just ignore this part and you have to look here, right? So you can, since there is a ground here, no current will flow through these terminals. So you can just focus on this part. But I will just draw the whole circuit. Let me start with M3 and M2. We have to find the resistance looking into here, so I will attach IX, VX. So this will be VGM, VGS3. So this is connected to V2, and that will have GM, VGS2, R0, 2. Okay, this is connected to ground. This is connected to gate, which is then connected to VGS4, R04. This is connected to gate, and this again MGM1. This is connected to it. So this is the equivalent circuit, but as you know, this is at 0, this is at 0. So this will be off. Then what do we have is, if I apply Ix here, so this is my R of 3, right? So my Ix, we just I write it as Ix is equivalent to Vx minus V2 divided by R of 3 plus Gm VGS3, right? That will be Vx by R of 3 minus V2 by R of 3 plus, since Vg is 0 and Vs is V2, I can directly write it as Gm V2. Gm V2. Now your V2, if Ix comes here, Ix should flow here, so I V2 will be Ix times R of 2. So my Ix is simply equivalent to Vx by R of 3 minus Ix R of 2 by R of 3 minus Gm V2 is Ix R of 2. Simplify, R of 3 plus Gm R of 2 is equivalent to Vx by R of 3. So this means Vx by Ix is equivalent to Gm R of 2 R of 3 plus R of 3 plus R of 2, right? Or let me call it as R drain 3, that will be RO3 plus RO2 1 plus GM. This will be my output resistance. Now what we have to find is, we have to find the answer in mega ohms. For that, we will have to find RO3, RO2, and GM. If we go back to the question that says lambda is 0.01 for every transistor. So your RO3 will be equivalent to RO2. So RO3 will be equivalent to RO2 will be given by 1 by lambda times ID. That is 1.01. The ID is 2 milliampere, I think. Let's just check. Let's check this 2 milliampere. So this comes out to be 50 kilo ohm, right? And again, Gm will be given by 2 times IDS KW by L. And that again is 2 milliampere and KW value is 1 milli. It is 4, that is 2 millisiemens, right? Now that you have these values, then you can calculate R3 and RO3 50 kilo plus kilo 1 plus gm. Gm is 2 milli, minus 3 into power of 3, that is 50 k. And then 1 is equivalent to 50k plus 50k into 1. So our train will be equivalent to will equivalent to that's what how much is it? And it's out to be 5 and double 0 times power 3, that is 5.1 into 10 is power 3, say into 10 is power 3, that will be 5.1 mega. So this is the resistance looking into the drain terminal of M3. Okay. Next is we have to find the minimum DC value of V3 with which the small signal output resistance is high. That means we have to find a minimum value for which device remains in saturation. Now if I have transistors, two transistors here, if I want to calculate these potentials, either both transistors are in saturation, so what will I do is, if this is, let's say, V volt, this is V1, this is V2. So I will write V is equivalent to V1 in saturation plus V2 in saturation. So this will give me my minimum value for which the both device to the output distance, that is Alright. So here we have to find the V3. It is given to us as V3. This is V2. Let's go back here. V3, V3, V2. So for the both transistors to be in saturation, then that means V3 min should be equivalent to, for this device to be in saturation, that is V3 minus V2 sat plus V2 sat. Okay, so if I see that VGS is equivalent to 3 volt, so VD sat for transistors will be 3 minus VTH is 1, that is 2 volt, right? So this is 1 second. to find the minimum value of PC value. Okay, we can just directly um, V3 minimum will be its saturation voltage, that is its VGS3 minus VTH, that we calculated as 2 volt plus whatever is the potential from the here to here, V2. It is 3 minus 1 plus 3 volt. V2 is 3 volt. That will give me 5 volt. We can also write in this way, your V3 minus V2, that is your VDS, should be equivalent to VGS, that is terms number 3, VGS3 minus its VTH, that is V3 minus V2 should be equivalent to, that is VG3 minus V2, its source is V2 minus VTH. This and this will go. And V3 and VG3 has been calculated, right? VG3, let's see, VG3 is 6 volt, VG3 is 6 volt, so V3 will be 6 minus 1, that is 5. No, right. So this is also a way to solve this. Okay, but this is the minimum voltage. Okay, now let's move on to the another question. Some few more numericals, current related to no current related to. So here, let me just go through quickly. We have details given here. Just keep in mind that for PMOS and NMOS, different PW by L values are given. 3A, 3B are identical, M1 and M2 are identical. Okay, okay. So I have to calculate R1 by R2 is equivalent to R3 by R4 such that IST of 2 milliampere flows through the transistors. ISD1 is given. So now ISD1 is given, I can directly apply the equation here. ISD1 is KW by 2L VSG minus VTH PH square. It's PMOS, right? So this is 2 milliampere. KW by L, it's given 1 milli by 2 VSG minus VTHP whole square. It will be VSG, taking the positive value, it will be, sorry, 3 point, this will be 4, yeah, this one. This is 2 plus VTH. P, that is VSG will be 3.5 volt. Okay, so now we have VSG. VSG is this potential to this potential, that is Vs minus Vg is 3.5 volt. Vs is 10, 10 minus 3.5, that is 6.5 volt is Vg. Now your Vg, what is your Vg? Vg is R2 divided by R1 plus R2 into Vd, right? So your R2 by R1 plus R2 into Vd is 10 volt, is equivalent to 6.5 volt. So 10 R2 is equivalent to 6.5 R1 plus 6.5 R2. That is 3.5 R2 plus 6.5 R1. That means R1 divided by R2 is equivalent to 3.5 by 6.5. That is 730, right? So R1 by R2 is 730. Similarly, you can find R2, R3 by R4, right? What we have to do for R3 and R4? Now, now that you know VGS or VSG, VSG is 3.5 volt, then that means this potential to this potential is 3.5 volt. So that means here as well, this is 3.5 volt, right? So from this potential to this potential, this should be 3.5 volt, right? Uh, you can now quickly go through it. And sorry, this is a PMOS here. But this is 3.5. Alright. So from this to this should be 3.5 volt, right? And again, this will be given by R4 divided by R3 plus R4. Okay. And this comes out to be 7 by 30. Okay. Find the precise value of DC output voltage as shown in the figure. We have to find this voltage. Again, if we go by the current mirror method, then what is the potential it should have? Directly this potential, right? Besides, there's the same current flows, right? M3 and M3 are, since M3 and 3B are identical, so it should directly have this potential. There was one mistake here. This is not 3.5 volt here. This is not 3.5 volt here because kW by L is different for these transistors. If you go on calculating it, you can just directly use this 2 milliampere formula. 5 by 2 milli VGS minus 1.5 whole square millivolt. That is 4, and this will be 16. 16, and it will take the root, it will be 4 plus 1.5. So this will be 5.5 volt. Okay. So directly, if you just directly, you can just directly say the answer for the next question is should be also 5.5 volt. Right. So let's just write a few things about it. For the same current, slow potential at drain should also be equal means increase, transistor should be identical. Okay, now that means VD3A is equivalent to V out, right? As I said, this grid potential should be equal to V out. And this VD3A is equivalent to VGS3A. For transistor 3A, we calculated just, let me just calculate again. ITS is equivalent to KW by 2L, VGS minus VTH whole square. This is 2 milli, this is 0.25 milli by 2, VGS minus VTH whole square, milli by 60 is equivalent to, this comes out to be 5.5. So therefore, the output is 5.5. Okay, we have done these questions a lot of many times. So that is gain AV is equivalent to the output by V in. Let's draw the equivalent circuit. I will draw the half of the circuit because the AC analysis VD is 0. That means this transistor is off, M2 is off. So there would be no bias here. So this will only act as a resistor. Simple resistor. Let me just draw the circuit. Now this is 0, so this will not be used. So this is the out. This is R1. Now, if we out, let me just let's use KCL. Out. This would be out by RO3B is equivalent to GM VSG plus Vs minus V out by RO1. V out by RO3B will be equal to GM VSG. VSG is minus times V in. Because VSG is Vs minus V in. Vs is 0, so this will be V in. Minus V out by RO1. So this will be given to us as V output by RO3B plus V output by RO1 is equivalent to minus G of V in. So this will be V output RO V output by, let me just write it first. Again, RO1 RO3B equivalent to minus V in. So mod of the output by the in is will be equivalent to GM RO1 RO3B divided by RO1 plus RO3B. That is GM RO1 parallel RO3. Let us just see RO1 lambda is equal. Yes, yes. So RO1 will be equal to RO2 and IDS is 2 million. RO1 will be equal to RO3B, that is 1 lambda time ID, that is 1 by 101 into 2 milli, that is again 500 times 50 kilo ohm. And similarly, your GM is KW by L VSG minus VTH, that is again 1 milli, and VSG is 2, VSG is VSG. Okay, so VSG is 3.5 volt, right? Uh, we estimate. Okay, then right here. VSG is 3.5 volt, and VTH is 1.5. So this will be 2. So 2 milli. Now your R, that is your gain, will be simply multiply the 2, that is 2 milli, and these are in parallel, 50k into 50k divided by 50k plus 50k. So this will give me 50k by 2, 2 into 50 by 50 equivalent to 50k into go, k and milli will go. It's 50, 1 by 2, so this will be 50. So gain will be 50. Okay, so this was a similar kind of question we had done before. The main important for part of the session was the current mirrors, and we just had a brief introduction to it and why should we use the current sources. Okay, I guess so the last of the session.